So, I will be explaining the behavior of a coilover suspension using the second-order differential equation. We know a coilover is commonly used in vehicles to absorb shock on bumpy roads. It consists of two main parts, that spring and damper. Spring provides restoring force, while the damper resists motion using the friction. So, we will derive the equation of motion by using Newton's second law. So we know Newton's second law is F equal to ma, and we assume m as double prime. For damping force is F equal to negative Cx prime, and spring force is F equal to negative Kx. So the total force is mx double prime plus Cx prime plus Kx equal to 0. So this is our second order linear differential equation (ODE) to describe the motion of the coilover. So based on the equation that we got before, we can create the ODE equation that is my squared plus cy plus k equal to 0. And then we use the quadratic formula, but we just focus on the nature of the roots. To find the nature of the root depend on the discriminant. So we assume this discriminant equal to D. So based on formula, D equal to B squared plus 4AC. And then after we replace quadratic formula with ODE equation, we got D equal to C squared minus 4mk. So we see here over them D greater than 0 is real roots, and critically damped D equal to 0 is repeated root, and under damped D less than 0 is complex root, and under damped is C equal to 0. So for all this question solution, describe how the coilover respond under different damping condition.
This slide shows the system constants for our coilover model. The mass is 1 kg and the spring constant is 4.324 Newton per meter. Using this, we calculate the natural frequency as the square root of k over m, which gives approximately 2.078 radians per second. Here, we define the damping behavior of the system. When damping is 0, it's undamped. At 1.234, it's underdamped with oscillations. Critical damping happens at 4.155, and beyond that, at 5.678, the system is overdamped with no oscillations. This slide breaks down how different damping types behave. An undamped system keeps vibrating endlessly. Underdamped ones still oscillate, but the motion dies out. Critically damped returns to rest the fastest without bouncing, while overdamped is slower but still avoids oscillation. These behaviors are key in real-world systems like car suspensions. Here's the visual. The yellow curve shows undamped motion, no energy loss, just constant vibration. Red one fades out slowly, that's underdamped. The purple curve settles quickest with no bounce, that's critical damping. And blue shows overdamped, smooth, no bounce but slower. Each curve highlights how damping changes system response.
For the discussion, by using Newton's second law, the system force are analyzed. Consider the damping force, spring force, and the net force. This leads to the development of the equation of motion for the system, which is a second order ordinary differential equation, which is ODE, which describe the displacement of the system over time. The equation is solved using the quadratic formula, and the behavior of the system is analyzed under different damping conditions, such as overdamp, critical damp, underdamp, and undamped. The simulation of displacement of versus time graph for different damping condition is a critical tool for visualizing the dynamic behavior of the system, showing how much each damping condition affect the system return to equilibrium. This analysis is essential in designing system like vehicle suspension, where a balance between minimizing oscillation and stabilization is crucial. In a damped system, the displacement versus time graph show a sinusoidal oscillation that continue indefinitely. This happens because there is no resistance or no damping force to dissipate the energy of the system. The amplitude remains constant, meaning the system oscillates back and forth at a constant rate. An underdamped system experience oscillation that gradually decrease in amplitude over time. This occurs because the damping force is present, but it is not strong enough to prevent oscillation entirely. The system eventually back to the equilibrium position after a series of diminishing oscillation. In a critically damped system, the system returns to the equilibrium as quickly as possible without oscillating. This is ideal damping condition for many mechanical systems, including vehicle suspension, because it prevents both excessive oscillation and slow return to equilibrium. In addition, to avoid oscillation, an overdamped system has a slower rate of equilibrium return. In the instance, the system moves slowly back to its stable state because the damping force is too high.